Let's talk Pascal's principle. This is also under the heading of fluid statics, statics meaning fluids at rest. So I want you to imagine a car hydraulic lift at a service station. Here's a picture of it. So what I've got in this container is kind of a U-shaped container here that has a single open fluid containing vessel. On one side, I have a tool that I can use to apply force downwards from, say, a human or from some other system. So I can push down there, and pressing on an incompressible fluid forces that fluid here to push up on something heavy like a car. Pascal's principle describes something really important here. I've got a contained fluid where pressure is transmitted undiminished to all points in the fluid, and including the walls of the container. So pressure 1 on the left side, here we go, let's add that in. Pressure 1 here on the left is equal to pressure 2 here on the right. Now because of that, and pressure being defined as force per unit area, I can take that statement about pressure and turn it into a set of ratios about forces and areas. So what's really cool here, Pascal's principle equates the amount of force required as, say, an input on this car lifting system to the output of force here. And because this area is small and this area is large, I can use a small force here and get a large output force here. Let's look at an example problem that applies Pascal's principle. It looks like this. So I've got a large piston in a hydraulic lift at a service station. It has a radius of 20 centimeters. That's on the left side. What force must be applied? I'm sorry, that's the right-hand side. What force must be applied to the small piston on the left of radius 2 centimeters to raise a car of a mass 1,500 grams? So I've drawn a picture here just to show that the lifting force on the car is going to be equal to the weight of the car. Let's just assume we're lifting the car at a constant velocity, so I need the forces to balance. That's how I got to the output for hydraulic system needs to equal the weight of the object. And for a 1,500 car, 1,500 kilograms, I am going to multiply that by the gravitational field strength, and I get that the car has a weight of almost 15,000 newtons. Now, bringing this over here to Pascal's principle, I am going to say, I'll use the picture up here, the force 1 on the input side to the system is equal to the ratio of the areas of the two sides multiplied by the output force, force 2 on the output side. Side note, I find it easier to remember Pascal's principle in this form rather than the form I've written down here. So I've solved for force 1, now let's substitute in all the values I need. Let's see, areas. These are assumed to be circular hydraulic cylinders, just because that's the way they're typically manufactured. So the area on the small side is pi r squared. The area on the large side, pi other r squared, multiplied by the force. Here's all those numbers substituted in, right? 20 centimeters, 2 centimeters, bam, bam. And we're multiplied by the weight of the car. We get that we need an input force of 147 newtons. 147 newtons becomes 14,700 newtons on the output side. Pascal's principle is all about fluid statics. That's how it works. Zoom out on that, give you a chance to pause and check out any notes you might have missed. Thanks, and good problem solving.